Hi, I'm Phil Porras, and this is a short overview of the FortNox security kernel and the motivations behind its design. OpenFlow has some very exciting potential to drive new innovations in intelligent and dynamic network security defenses for future networks. In fact, long-term OpenFlow could prove to be one of the more impactful technologies to drive a variety of solutions in network security. However, OpenFlow is not a game changer yet, and here I'm going to discuss some of the security implications to OpenFlow that early adopters will likely consider as they ponder its use in secure network environments. Here, we'll focus on the question of how to reconcile the dynamic nature of OpenFlow's network policy generation with that of our traditional notion of classic network perimeter defense. Here is a quick summary of the classic notion of network perimeter defense. Secure network operations are founded on the principle of a well-defined security policy, which is instantiated specifically for the target network topology, addressing all of its components, servers, applications, etc. The security policy is vetted for completeness, and the network configuration is vetted for compliance to that policy. The policy must be implemented consistently by the network policy enforcement infrastructure, such as the firewalls and access list that govern communications to and from the network. And when the network is operational, it should be tested and monitored for policy violations. Finally, those elements that operate with an ability to change the network security policy must be trusted, and when they do so, these events should be audited. OpenFlow's approach to producing and managing communication policies is much more dynamic. It embraces the paradigm of highly programmable switch infrastructure, which continually redefine the network's flow policies based on the stream of incoming requests. OpenFlow applications convey flow routing decisions through flow rules. If you think of a flow rule, which in the end defines whether two endpoints can communicate, as a security policy decision, you'd be right. And the current set of active flow rules in the OpenFlow switch effectively defines the network's security policy. So, from a security perspective, what we'd like to do is provide an OpenFlow implementation that can first and foremost be relied upon to enforce security constraints imposed by our operator. Second, we need to maintain the powerful dynamism of OpenFlow applications to produce optimal flow decisions, as long as those decisions don't conflict with the network security policy. And finally, as this is OpenFlow, it would be ideal if our solution would enable one to dynamically extend the network security policy, for example, to combat newly detected threats. FortNox is an extension to the latest Nox OpenFlow controller. It extends Nox by adding a non-bypassable mediation service, which performs inline vetting of OpenFlow application flow rules against the current set of network flow constraints defined by administrators or OpenFlow security applications. I'm now going to enumerate the key security features and principles that are included in FortNox. As FortNox's central purpose is to mediate new candidate flow rules against the existing security policy, it must do so without interference from the flow rule producers. In short, Nox is not, by default, isolated from C-based OpenFlow applications. Rather, for performance purposes, they can operate as libraries in the same process space as the controller. However, the FortNox controller executes independently, in a separate process space and ideally from a separate user account. To facilitate this, we've added a proxy wrapping service such that all OpenFlow applications, including legacy C libraries, will operate in their own process space, preferably under different user IDs. FortNox incorporates the notion of role-based authorization among its role producers. By default, FortNox recognizes 3 authorization roles and includes an ability for operators to add subroles to extend the authorization hierarchy. The network operator role is for human administrators and is granted the highest authorization. Operators define the authoritative base security policy and can update this policy at any time through a FortNox Operator Console application. OpenFlow security applications can extend the security policy with additional flow rule constraints using FortNox's security directive APIs. A security app monitors the network's live operation and injects new flow rules to constrain traffic producers who are perceived to threaten the runtime integrity of the network. Legacy OpenFlow applications operate as before, with the exception that when an app produces a flow rule command that conflicts with the security policy, the app's rule is rejected. We make no assumptions that the OpenFlow app is even aware of the current security policy, and security enforcement does not depend on the absence of our OpenFlow applications being free from vulnerabilities, errors, or from complex interactions with other apps. Authorization roles determine what rule priority a producer's roles will be assigned, and FortNox will use these priorities to resolve security policy conflicts. FortNox uses digital signatures to implement strong authentication and integrity of rules provided by a rule producer. At setup time, a producer may export their public key, which the operator can then assign to a FortNox authorization role. Nox's flow rule data structure is augmented with an additional digital signature field. If the field is not defined, then the role is by default assigned the OpenFlow application role. FortNox operates as an inline flow rule mediator, vetting all insertion requests against the current existing set of flow rules. Inline rule conflict detection is performed using our algorithm called alias set rule reduction. A conflict is said to arise when a candidate flow rule is determined to enable or disable a communication flow that is otherwise inversely prohibited or allowed by the current set of existing flow rules. We demonstrated how alias set rule reduction works in our first demo video on security constraints enforcement, and we published this algorithm in the 2012 SIGCOMM workshop Hot SDN. When a candidate rule is found to conflict with the current existing set of flow rules, FortNox employs a conflict resolution policy to determine which rule should be accepted and which should be discarded. FortNox consults the digital signatures of the conflicting rules to determine which rule is associated with a higher authorization role. In the case of the flow rule add or modify commands, if the candidate rule is signed with an authorization role greater than the existing rules in conflict, then the update is allowed. If the candidate rule is signed with a lower authorization role, then the candidate rule is rejected. And when both roles are found to have equal authorization, then final resolution is decided by configurable policy. The candidate rule may be allowed to override the existing rule, or it may be rejected, to force the producer to first explicitly delete the existing rule. In the case of rule delete commands, authorizations are strictly enforced. You can only delete a rule of equal or lower authorization. The goal of distributed policy synchronization is to ensure that when the controller alters the flow policy across the network, the modification process reaches a synchronization point at which we know that the intended policy is correctly and completely inserted. FortNox extends Nox to request and track barrier callback messages, and tracks switch callback notifications when flow rules are garbage collected. Barrier messages enable FortNox to synchronize flow rule insertions across a set of switches, and it uses the switch's flow removal notifications to manage its internal flow table state. Finally, accountability is a key security function for nearly all sensitive computing environments that must satisfy government or corporate compliance regulations. In support of this function, FortNox provides a security logging facility, which stores an audit trail of all flow rule insertions, rejections, deletions, and modifications. The audit log includes the digital signature for each flow rule, allowing strong individual accountability among the flow rule producers. To put it all together, here is a diagram showing the central interface of the standard Nox controller. Nox operates as a mediator between Python and C-based OpenFlow applications and a set of OpenFlow switches. Using Nox, OpenFlow apps can hook in to network events, gain access to traffic, and initiate flow rule insertions to a switch. To communicate flow rules to the switch, the OpenFlow app uses a central interface within Nox called send OpenFlow command. And here is a summary of the components we've integrated into Nox to create the FortNox security kernel. As we discussed, to ensure the runtime integrity of FortNox as a security policy mediator, we created an IPC proxy. A legacy OpenFlow CLib can be wrapped in the OF client proxy, which then relays Nox API request to the proxy interface embedded within FortNox. We've also developed a security API that allows network security applications to send high-level threat response requests to FortNox, which then translates these requests into OpenFlow rules. In demos 2 and 3, we present 2 example security applications that use FortNox security directives to combat live malware attacks. The red lines here indicate that the messages exchanged can be digitally signed with the private key of the application that produced the OpenFlow command or security directive. We've added a role-based source authentication module that validates the digital signature attached to the message and assigns the message with the priority that is appropriate for the authorization role for that digital signature. The State Table Manager tracks the disposition and status of all flow rules active in the network, which it maintains within a local aggregate flow table. Here we depict the notion that this aggregate flow table tracks the role authorizations associated with each role, which it maps internally to flow rule priorities. A FortNox conflict analysis module evaluates each incoming application layer command or candidate flow rule against the state of the aggregate flow table. A separate switch interface module is added to set and track barrier messages and garbage collection callbacks from the switch. This information is propagated back to the State Table Manager. Finally, an OpenFlow security audit log service is added to record flow rule state changes, conflict resolution decisions, and switch garbage collection actions. And that's an overview of the FortNox security kernel. Thanks for your interest, and please visit www.openflowsec.org for more information about FortNox, including our reports, our demos, and software releases as they become available. Also, we'd like to thank the Army Research Office and DARPA MRC program for funding this work. And finally, if you'd like more details about this work, we have a publication which focuses on FortNox at the SIGCOMM Hot SDN workshop in August 2012.